Okay, welcome everyone. Thank you very much for making the long way here to the Palace Hotel. I know it's like a 10 minutes walk from the Moscone. So I really appreciate you making the way here. That shows dedication, so thank you very much. First of all, I want to start off a little bit, what am I going to talk about today? Because if you see this and you think like this is not what you expected, please feel free to change rooms. I don't want to keep anybody here that doesn't get what they expect. So first of all, I'm going to start with Cloud Spanner architecture recap. So I want to get everybody on the same page. What's the terminology? How does Cloud Spanner work under the hood? Okay. Second one is the schema and workload optimization. So I'm going to talk about common challenges or things that we see when developers and operators work with Cloud Spanner. So I'm going to address those. I'm going to talk about multi-region configurations, what are they good for and what does it mean behind the scene. And then at the end, I also give some recommendation about related sessions to this one. So first of all, a little bit about myself. I'm a developer advocate for the Google Cloud Platform. I'm concentrating on storage and database system with like a very deep passion on Cloud Spanner. So I've worked with Cloud Spanner for over a year now. I've done the keynote demo last year where we demonstrated like the scale of Spanner, and today and in this next 18, we're basically looking at like manageability of Cloud Spanner. What is a cloud developer advocate? We understand ourselves to be the bidirectional interface between developers, operators that build on our platform and the developers and operators that build the platform inside Google. So please, please, please feel free to reach out to me. You find me on Twitter, you find me on other channels. If you have challenges, if you have recommendations how to do things better, we have always an open ear for that. All right. First of all, I want to check a little bit, do a pulse check who is here today. Who is a developer here in the room? All right, that is awesome. That's my audience. Who is an operator? Okay, ITDM, CXO. Okay, we have a couple. Welcome. So that's very good. Who is using already Cloud Spanner today? Oh, awesome, awesome. Okay, so half the room is using it. So for you, it's basically a refresher at the beginning. And then I hope I can show you a couple of tricks how to get the most out of Cloud Spanner. All right, so if you read the statement about Cloud Spanner, we are a relational database service that provides strongly consistent transactions and that scales horizontally. Now that sounds pretty awesome, right? So if you look at these things separate, you have that around today, like in many, many phases. If you look at strongly consistent databases, there are like relational databases out there for 40 years plus. Very like hardened and everything, but they don't have the scalability aspect. Now, if you take the transactional, the consistency away, you have like for 10 plus, 15 plus years, the so-called NoSQL databases around that give you the horizontal scalability, but you do have to do sacrifices on the consistency. Now, Cloud Spanner tries to combine these things, and I'm going to talk about how we are doing this. So let's start with an architecture recap. First of all, about the terminology. There are a couple of things that are like very familiar to people that work with relational databases. So we have an instance which basically gives you a resource pool, your nodes that you have and how much data you can store in an instance. Then you can store, I think, up to 100 databases in an instance. And in each database, you can store up to 2,048, I believe, tables. Now, these are the constructs that are visible to everybody outside, like if you use Spanner, and that's are the construct that you're used to if you work with a relational database. Now, to provide the scalability in Cloud Spanner, we have another construct which is hidden from you, and that is called a split. So basically what we are doing, all the tables are like ordered by lexicographically by the primary key. And then we divide them into chunks that we call split. And that allows us to scale. We can basically hand these chunks between the resource nodes that we have available and make them responsible for different of these splits. And by that, we get these, the scalability that we see. So if you look at like kind of an architectural view of a regional instance, you have 3 zones for a regional instance. and you have your compute resources and your storage resources. Now they are like independent scalable. We have some restrictions how many nodes you have to have at least for a certain amount of data. So per 2 terabyte, you need at least 1 node. So you cannot scale further down than this restriction. But other than that, you can scale to thousands of nodes, even if you have only a couple of terabytes of data. Now, in your zones, you have basically the computes. For each node that you buy from us in the Cloud console, you get this node 3 times replicated, once in each zone. And then you have the storage, which again is also replicated, which is not illustrated here in this graphic. But the storage is also replicated to like, I don't know how many nines of durability. Now, one thing that we need to basically organize and have this strong, consistent system is something to basically synchronize like who is responsible for a certain part of your data. And we never, never, never want to have 2 compute resources be responsible for the same data. Because that is where inconsistencies come in. So we needed some kind of mechanism to make sure that we never have 2 owners of a data piece. Now, one way to do this is with communication. But communication, especially if you go further away from each other, so if these zones are a couple of milliseconds apart from each other, you basically incur round trips. So if you look at traditional databases, they ensure like consistency with the 2-phase commit protocol. And for the 2-phase commit protocol, you need multiple round trips basically to ensure this consistency. Now that is very expensive and it wouldn't scale, obviously. So we needed another way to ensure the consistency while being able to remove this additional communication. And the way that we did this is that we invented TrueTime with the spanner system. So what is TrueTime here? So now if you look at TrueTime is basically a system that quantifies the worst possible error or drift between clocks all over the world. So in all our data centers, we have so-called GPS masters and time masters, or atomic clocks, which are synchronized through GPS. And then we can quantify how much they drift at most. And by this, we are able to basically choose this timestamp interval, where we can say that the lower end of this interval has passed everywhere, and the upper end of this interval has passed nowhere. So you see there, if I read like the TrueTime now returns an interval T1 and T2, where T2 is T1, so the lower bound, plus 2 epsilon, which is basically our security in terms of like the drift that we expect. And then so T1 is guaranteed to be lower than the value of a global clock at the instance when now finishes executing. So when you get this interval, this has definitely passed. And T2 is guaranteed to be higher than when this TrueTime turn now starts executing. So we use this interval, this TrueTime interval, to ensure strong consistency across the database. And not only within one region, we can do that across regions even. So let's look at a little bit about like how does it work. Let's start with a simple life of a query. So here in this case, I want to do a consistent read. So I basically want to get the latest state of my database. And we choose here a select statement. So I have to select from event where the name is next 2018. Now the request comes in from your client. It goes to a follower because that's the one that is closest, the follower of the split. So you basically have the Paxos group where you choose a leader and then you have 2 followers. And then the leader is basically who holds the hold-throughs of your data for that split. Now the request comes in to your follower, and the follower sends a request to the leader of this Paxos group and says, like, hey, do I have the latest data? And if the leader sends back and says, yes, like this timestamp is what I have. If you have this timestamp, you have the latest data. The follower serves the data back. So there's no data going between the leader and follower here. It's really just to check, do I have the latest data? Now, in the case that the data is not there yet, basically what the leader responds is saying, like, hey, you don't have the latest data. This is the timestamp of the latest data. Please wait that out till you see that timestamp. And once you see it, you can serve the data, because then you know that you have the latest data. All right, we have also another construct in Spanner which we use for optimization, especially if you use a global instance and you want to have fast response times. You can do something which is called time-bounded reads. And time-bounded reads are not consistent, not strong consistent. They are consistent. They are consistent time-bounded reads, but they are not the latest ones, basically. Now, for a time-bounded read, so-called stale read, you can define a boundary. You can say, like, OK, I accept data which is up to, like, let's say, 15 seconds old, or you can actually define an instance of time within 1 hour. So we allow up to 1 hour that you can go back in time with a time-bounded read. And in the time-bounded read, in like many cases, especially if you use a 15 seconds time bound, the data is already there for your follower. Because if we have a transaction, not as directly as part of the transaction, but immediately, like when this transaction is happening, we are sending out that data to all the followers. So they have that actually pretty quickly. So here in this case, if we do a request and we say, like, we allow 15 seconds old data, the follower basically checks, do I have, like, if the data hasn't changed for a while, we basically send a heartbeat to update, like, this is the latest data. Then we can say, like, OK, I have the data. I don't need to go to the leader. I can directly serve that data, and I leave the leader alone, which is pretty amazing. Now, I want to look into writes. So I mentioned one thing is, like, two-phase commit is something that is expensive. Another thing which is expensive is logs. So Spanner was designed in a way you only use what you need. So if you don't need certain things, you don't pay the penalty of, for instance, a two-phase commit. So as an example, if you, like, go into a traditional database and you want to have, like you do a transaction, but you only read something in this transaction, you don't actually write something. You still acquire logs, and you still have, like, certain two-phase commits in some of the systems. And you basically pay the penalty for that, even though you haven't maybe not even changed any data. Now, in Spanner, we allow for certain kind of transactions to actually be logless. And we allow for certain kinds of transactions actually for logs to be shared. So here's an example of a single split write. In a single split write, let's say it's a point update, and let's also say it's a blind update. So I'm not reading anything. I just say this value with key 100, I want to write A. As you see on the left side, I want to write for key 100 the value A. So what's happening, basically, this comes in, let's say, through the API front end. And we do a split and leader lookup. Now, this is very heavily cached. I left it in here in the graph. But basically, that the round trip that you see to the zone master is, like, very rarely happening, because we are caching very heavily in the front end where the splits are living and where the leaders are for these splits. So we basically get back who the split leader is. And so we're sending to the split leader the commit request. And I would actually change the slide right now because there's an error. This send commit request goes to the split leader, not to the other replicas. I apologize for that mistake. Now, what the split leader does, it basically acquires a write log and then assigns a true timestamp, waits out that time. While this waiting out this time, we send a persist request to the other replicas. As soon as we get a majority of acknowledge that this change was persisted, we basically say, OK, quorum is reached. We just wait out the true time upper bound. We know at that time it's persisted, and then we send back to the front end or to the client that the transaction was successful. Now, I mentioned this is a blind write. And in a blind write, we can actually share the write logs. So if we have multiple blind write transactions, they can share the write log, which is amazing. So you can actually, we just use true time for the ordering, and they are not, like, conflicting, and we can share the write logs. All right, so let's make that a little bit more complicated. Now, in this case, we have a multi-split write. So here, what I'm doing is I'm reading the value from the key 100. I'm writing a value to key 100, the value A. I'm writing a key value to the key 300, the value B, and to the key 400, the value C. Now, again, we do the split leader lookup for our read, because that's the first thing that we send. Now we send the read request to the split leader of the zone A split 0. That is where my key value 100 lives and the leader is. And the leader acquires a read log. Read logs, again, can be shared. And sends the result back. Now on my client, I do something, and then I'm sending the writes. So I'm sending the write for 100, for 300, and 400. So before I send that, of course, I have to do the lookup where the leaders for these values live. Then I send the commit request to my split leader of the zone A 100, split 0, which is my key 100 split leader. Then I send it to zone C split 2, which is my key 300 zone and split leader, and then to zone B and split 3, which is my zone leader for the key 400. Now, what the front end is doing as well is when we do this write transaction, is it is choosing a leader of this multi-split transaction. We need basically a leader who is in control of this transaction. Now, since it is multi-split, we actually have to do two-phase commit. Right? In the single write, we didn't have to do two-phase commit, but since this is multi-split, we actually have to coordinate between the different Paxos groups, so we have to do a two-phase commit. So when we send the commit request, each of the split leaders is requesting the logs. So I basically do the write log for the zone B, I write log for the key 300, and I do also verify the read log for the first one that I did. I'm also writing this key, so I'm also requesting a write log for that. And then once all these logs are required, I send basically that back to the chosen leader or coordinator of this transaction. So now what is happening once I have all these confirmation that my logs are required and they are still valid, the leader basically assigns a true timestamp to that transaction, records the commit to some replicas, and once it gets a majority of this in their Paxos group, it sends it out to the other split leaders. And then the other split leaders is recording that commit to the replicas in their Paxos group. And as soon as they have the majorities, they send back, they basically are prepared for that commit. And then once this is done, basically we know that the commit is done. We have before, so the first phase was basically verifying that we have all the logs and that we can get all the logs. The second phase here you see is basically, yes, please commit that transaction. We have all the logs, so we can commit this transaction. We again wait out the true time uncertainty and report back the commit success to all our other participants of that transaction. And then, like in parallel, pretty much the mutation is applied. Now, if there's any point in time where we have a log conflict, for instance, I acquire a read log and another transaction has a read log as well, and then I want to upgrade that read log to a write log. But since the other transaction has a read log, I cannot upgrade it to the write log. What is happening in Spanner is basically we do a wait and round. So basically what it is doing, it is going to cancel, abort basically the transaction that is younger. So the front end knows the ordering of the transaction, and if they see like there's a looming deadlock, we are basically aborting the younger transaction, let proceed the older transaction, and then we just retry the younger transaction that we aborted. All right, so with that knowledge, what are the things to look out for when working with Cloud Spanner? So first and foremost, and that's one of the most straightforward ones, sometimes still missed, is the choosing of the right primary keys. So primary keys, I mentioned in the beginning, the tables are ordered lexicographically, or for the mere models, alphanumerically. So if you have something which is monotonic increasing or decreasing, you basically add to the last split or to the first split. And as mentioned, one split is always owned by one computer source. So if you always add to one split, you basically exhaust the computer sources on that split. So the recommendation, use well-distributed primary keys or composite primary keys if you can. Also, look at reordering your table if you see that that can help in getting your key more distributed, your compound primary key more distributed. Another thing is be careful with interleaving. So interleaving can be powerful. Interleaving is a technique where you basically make sure that the data lives on the same split as the parent table. So you interleave it in the parent table. They have to share the same primary key in the beginning, so the same primary key prefix. And then it is interleaved and stored on the same split as your parent row. Now, the danger is if you have one parent row and a lot of data which relates to that parent row, you basically, again, end up with all the traffic to that data, to that child table in one split, which also leads to hotspotting. So be careful with that. It is a technique to speed up certain queries, especially if you need to do like some kinds of fast lookups for certain data where you want to benefit from data locality. You can use interleaving, but be careful with it. Same applies to indexes. So indexes are just tables in Spanner. So if you index a monotonic field, you get in the same problem. You get also into hotspotting. So be careful there. Use like an application level sharding key prefix, or something that is natural in your table that you can use to prefix your indexes. Now for complex transaction. So one of the things is Spanner basically logs on cell level. So if you have like columns and rows, like the log level for Spanner is on a cell level. But if you do, for instance, a read-write transaction where you select on a non-key column, then your entire table for that column is locked. Because we don't know, like, what is the range, like how many actually it could be. We also log for new rows inserted or for any rows that are updated, which could be qualifying for that filter that you set on a non-key column. So we're basically locking the entire column. And with this, you could run into basically contention for your writes. So you be careful with this. A good strategy to do this is, if you can, use a primary key in your filter so that you basically can filter down on the primary key, which allows that we don't do a full column table lock. And the other thing is, if you can, do lookups, or so like filtering before you do actually the read-write transaction. So a good technique is basically doing a read-only transaction before your read-write transaction. Get basically the data that you really want to modify, get the primary keys of that, and then use that and verify that the data hasn't changed in your read-write transaction. And then you have a much smaller scope of your transaction, and by that you avoid a lot of the write contention. So to that point, use read-write transactions only if needed. So read-only transactions are actually lockless. So read-only transactions just use the true timestamp. And we don't do any logs. We don't do a read log or anything. The only time you actually acquire a read log is inside a read-write transaction if you do a read. Otherwise, you don't acquire any logs in your queries or transactions. Now, another thing that we see in terms of like read contention, where you have a lot of data like hotspotting basically during reads. One of the things is if you have popular items. It could be, for instance, a counter. For a counter, we recommend to shard the counter if you need one. It could be a popular item. Let's say you have like a social graph in your Spanner database, and you have like that star that everybody looks up and wants to get the latest news. So to avoid these kinds of hot data points, one technique that you can do is replicating during writes. So you basically, when you write, you do RE replicas, and then you enable the read from these replicas. These writes are transactional, so you don't get the inconsistency in there. Or if you can, look at your schema if you can do things like reordering columns to avoid these hot data spots. Another thing, indexes. Consider how you define your indexes. Also, the same is for primary keys. Spanner always scans from the top of the table. Okay, so if you have like your index ordered ascending and you ask for that index for, let's say you have like an index on updated and like some sharding, up-level sharding to avoid hotspotting. And you want to have the latest updates on certain kinds of data. And you have your index defined ascending. the index doesn't help you. Define your index descending so that the newest values are at the top and you don't need to scan the entire index. Another important thing, since Cloud Spanner is a distributed database, we don't have optimizations that you find in single machine databases. So if you look at indexes in a single machine relational database, the way that indexes are implemented, if they are implemented performantly, is that they are actually pointing directly to the data point on your disk or in memory where that data lives. Now in Spanner that is not possible because that data could live on a different node. Like the index that you have might be in a different split than the data actually that you're accessing with your query. So the only thing that we can do here is we do actually have to do a back join to your parent table. Now to avoid this, what you can do in your index definition is using something like storing clause. So the storing clause are columns that are not indexed, but that you basically attach to your index that will be carried around with your index and might avoid a back join to your parent table. Now, again, like the things that we also discussed during the write contention apply also to read contention. Consider reordering columns for better distribution. Introduce app-level sharding to basically avoid hotspots. And then the other thing is also always to keep in mind, use indexes wisely. So indexes are coming with improved read performance, but at the cost of reduced write because they are spanning multiple splits. So pretty much if you have an index defined, unless it's an interleaved index, you always will have a two-phase commit during your writes because you have other splits involved that needs to be updated. Okay, so choose them wisely. Not always the indexes help. Okay. And they also come at the storage overhead. So this is also something to consider. Now, if you look at schema design and life cycles, so one of the things that we see, especially if you look at like a continuous integration and delivery setup, one thing that is like done like quite often, actually, scarily often, is to do like schema changes with like continuous delivery, and if you deploy like multiple times, maybe even during development, especially. If you deploy multiple times per minute, for instance, you get all these schema changes up per minute. And now what happens is actually Spanner is built in a way, Cloud Spanner is built in a way to serve live traffic while schema changes are ongoing. So our biggest primary concern is we want to serve live traffic while we also allow online schema changes. So we basically take a hit, we accept a hit on the schema changes to be propagated. But for that, you get the live serving of your traffic. Now, there's also another thing. Basically, the schema changes are done sequentially. There are preparation phases which are done in parallel while your traffic is going on. And then at the point that we do the switch over, we choose basically a true time timestamp. They are transactional. We choose a true time timestamp. At the point that we switch over the schema, we are aborting all the transactions that are in flight at that point that would conflict, which basically would span two versions of the schema. Now, another point to consider is we are keeping schema changes in memory for about an hour, a little longer. The reason that we are doing this is we are allowing time-bounded reads. And in time-bounded reads, you can basically go back in time, and by going back in time, you could actually hit an old schema. So we still need to be able to serve the traffic for that old schema for time-bounded reads. So keep that in mind. It is basically incurring memory pressure on our nodes because it's taking up space if you do a schema change. And so we are basically kind of lowering the amount of schema changes that you can do per time unit. So really consider that when you're doing schema updates that you don't do them too often, like in a short amount of time. Also, one thing to mention is if you create indexes, for instance, in your schema changes, there are, of course, like as in other databases, they need to be backfilled, especially in Spanner, because they are like just normal table. We basically need to backfill these indexes depending on the amount of data that you have. That can take minutes, hours, or sometimes even days if you have like a lot of indexes that you need to backfill. All right. A couple of things on the application design. We introduced recently the commit timestamp, so you can now add a column to your schema that automatically that you can say in your client, please fill that column with the commit timestamp. You can use that, for instance, if you update any data, like to this be automatically filled. I put it down in Java and Go. We have that for many, many other languages as well. You see there, you basically define like a constant that you provide in your write transaction, and it will be automatically filled on the back end with the value of the timestamp. One important thing is also to benefit from caching, from query caching, and to avoid, of course, SQL injection attacks. Please use bounded parameters. That these allow you to basically, and allow us to do more efficient caching, and by that basically lowering also response times because we don't need to create a new query plan every time. All right. In terms of like bulk data imports and exports. So on the one hand, we have an Apache Beam connector, which is doing all the hard work for you to do optimizing the export and import of data. We also have it just recently, last week, I believe, announced that we have import and export built into Cloud Console. So what you can do now is you just click a button, you say your Google Cloud Storage destination, and say like, I want to export there, and then you can basically import from there as well. A very long-awaited feature from our customers. So we're really happy that this is now available, and it will actually improve over time as well. Now, if you're somebody like me who wants to actually understand and do all the bulk loading and importing and exporting yourself, there is a trick to get the maximum throughput for your imports and exports, or especially for the imports to avoid the write contention. I have a video series around that, so please feel free to follow up on that. But basically what you do is you load a large amount of rows into cache. You sort these rows by your primary key. That can be a composited key. You basically sort that by then. Then you split them into chunks, into distinct ranges of your primary key chunks. And then you send those chunks in parallel. Now, somebody might say, like, wait, didn't you say like not monotonic increasing and decreasing primary key? Why are you sorting? The reason here is you're sorting and sending in parallel all these chunks, which basically means they go to different splits. There might be some overlap, but Spanner will recognize that during time we do load balanced optimizations, load balanced splitting, load balanced handover of responsibilities for splits during your traffic, so we can actually optimize that. And since you send a bunch or many of these sorted ranges to Spanner, we can actually get a really high throughput. So I was able to get like I think 12x speed up by just using that technique of importing data. Another thing which we recently added is tracing, which is integrated directly into Stackdriver, and I'm going to demonstrate that in a little bit. So basically that allows you to get some insights into where is your query low. Is it actually Spanner that is like taking a lot of time? Is it maybe on your client side, which uses a lot of time, and you can actually optimize on the client side? So Open Sensors allows you to do some tracing there, and we actually, if you get these IDs for your traces, they go back into our system. So we actually can trace certain queries that you have found that are slow on our side. We can actually use the UID and trace them back in our system and see what was going on. So that is actually pretty powerful. I encourage everybody to check it out and use it, and I'm going to show it in a little bit. All right, so let me actually show that at the first time. So I'm going to switch over to my demo laptop. So basically, how are you setting up tracing in Cloud Spanner? I hope is that visible, or should I make that a little bigger? Let me get that away. All right, so basically to get Open Sensors tracing, this is in Go. I apologize for anybody who's not a Go person. but currently my favorite language. So here in Stackdriver, you basically define a new exporter with some Stackdriver options. So in this case, the project ID and some attributes that you define. I basically attach some labels to my traces. I want to have the demo that is running and the region where this is running in this client. And then I set up some views and register that exporter. So that basically is all the setup here. Last but not least, we apply a config for this trace and say like, okay, how many traces do I want to get from all my requests? So you see here, like I want to have 1% of my requests as traced, and then these are sent to Stackdriver. Now, how does it look like if I do my actual query? So in my actual query, let's say I'm doing write for a sequential row. So I do a sequential write here. So I define a span. I'm starting that span, which is basically the containment of my trace for round trip. Let's say it's that way. I'm ending that span when the function is left, and then I'm using that context that I'm using here and passing that context basically down in my library. So this is really important if you use Go, that you use the same context and basically just wrap the context if you need some other qualities. So here, for instance, I'm doing a context with a timeout where I say, like, if after 5 seconds it doesn't come back, please cancel that, that whole thing. So I'm wrapping basically the context that I'm getting in my function into this timeout context. And then at the end, that's pretty much it. I don't have to do anything else. Like all the open census tracing is already supported in the library. It's literally these two rows up here, which enable the tracing. Now, how does that look like in my Explorer? So we can see here, for instance, all the traces that I have collected. Let's update this and see if this is still running. So we see, okay, this is still running. It shows you basically what are the times here for these traces. Now you see that they are pretty much like 3 lines kind of in response time. And the reason for this is actually the most upper line is clients running in Asia against a Cloud Spanner instance in the US. The middle line is my clients running in Europe against my Cloud Spanner instance in the US. And the lowest one here, which has like very low round trip times, is my clients running in the US in the same region as my Cloud Spanner instance. Now, the great thing that you can do here is you can pick one of those and show events, and it shows you basically, okay, I'm acquiring a read-only session, I acquired a read-only session, and then I'm going to Spanner and do the commit, and you see the 200 milliseconds here. Now let's see if I can maybe find something else. So here you see, for instance, we are iterating, we're doing a sequential write. You see the things that are going on. If I'm going a little bit further down, let's see if I can find one. Yesterday I found a really nice one which showed me that, for instance, if your session pool is too small and it needs to require a session, then you see basically it's like, okay, I'm waiting for a session, I'm waiting for a session, I'm waiting for a session. Oh, now I got a session. So the entire query took like, let's say, 500 milliseconds, but the actual spanner part of it was 5 milliseconds. The 495 milliseconds was the client trying to acquire a session. And you can fix these things on your client side. So you basically get insights into where is the problem. Are my queries slow, or is actually my client not optimized for the things that I'm doing with it? All right. So the next thing that I want to talk about is multi-region configurations. So we have 2 offers right now. We have a multi-region continental, and we have a multi-region global. Both of them give you a 5 nines SLA. So the regional instance gives you a 4.9 SLA. The multi-region gives you a 5.9 SLAs. Now, what is a continental multi-regional instance? You get a full copy of the database in 2 regions. You have the paxes that I explained earlier across 3 regions. I'm going to go a little bit in more detail in a second. And it is available even if one of your regions, your read-write regions, becomes unavailable. So the same applies for the multi-region global, whereas for the multi-region global, you add 2 read-only copies of your full read-only copies on 2 more continents, in this case, Europe and Asia. Now, how does it look like? For multi-region continental, you basically have a region 1, I have a region 2, and then you have a so-called witness region. Now, the witness region has a log store, but it doesn't have a copy of your data. And the witness region is basically somebody who has voting rights, but cannot serve data. Now, why do we need this witness region? We need it actually for the high availability. Now, let's assume like your region 2 becomes unavailable, right? If you only would have these 2 regions in your quorum, you cannot really get a quorum. So you could have like a split brain. You don't want that. So you need some kind of like a third region to get the majority in your votings for the Paxos group. And the witness region has this function for you. So now if region 2, for instance, goes down, we can still serve data from region 1 because the witness region helps to have the quorum for the transactions. Now in the global setup, you basically have region 1, read-write. You have another region, read-write in the US in this case. Now for quorums, again, you also have a witness region. Depending how far they are away from each other, you basically incur the round trip times for your transactions, especially in the two-phase commit. And then you have the read-only regions, which are on the right side in Europe and in Asia. Now, what do the read-only regions bring you? They bring basically, first, they are there to serve data. So not always you have to ship data basically from your read-write regions. Second, if you use stale, time-bounded, consistent reads, these can be served directly from your read-only regions if we have the latest data there. So if you use like 10 seconds, you're pretty much safe to use that. So in the case of writes and consistent reads, so you see the blue lines on the right is a strong read. Now, if we go basically in from a client in Asia, goes into the read-only copy in Asia and asks like, hey, I want to have the data. So what we incur is this round trip time to the read-write region and ask like, hey, do we have the latest data? Then we get the response and we serve the data from Asia. Now, if you have a write, we don't go to the read-only region. We go directly to the read-write region, so to where the splits lives in the read-write regions. Now, if a US client comes in, it's pretty much the same as you have for a regional. Now, if you have time-bounded ones, again, you basically go to your read-only region. If it is within the bound that you have that data already, you can just serve it without even consulting your read-write region. Okay, so before I go in the related session, I just want to show my last couple of minutes a couple of things. So one that I want to do is I want to start a demo. So what I built here, I just want to explain it a little bit. So if you go to the showcase in Moscone West, and you go to the Cloud Spanner showcase, we have one that basically illustrates the manageability of Cloud Spanner. And then there's station 2 where you can play with scaling the number of nodes out and in and scaling the throughput up and down. And it shows you how quickly Spanner actually adapts to changing throughputs, as well as how quickly nodes that you add become available to serve your workload. It's pretty amazing. So I've built this app, or basically the backend, by having clients running in Kubernetes. And they are attaching to a PubSub session. And then I can use PubSub to send a message and instruct them how much traffic to serve, how much traffic to send against Cloud Spanner. So how much read traffic, how much write traffic, how much time-bounded read traffic. Now, I found that very powerful because it is a very easy way to have an interface to communicate with, especially like the agency that built the station and the backend that I was building. So in this case, what I want to show here is I've set up a system where I want to show you the differences between a multi-regional continental and a multi-regional global instance in terms of like kind of what the latencies are that you're going to see. So let's have a look here. I'm going to change to, let's say, multi-region global. Now I'm going to save these changes. Okay, you're going to go. Oh, thank you very much. Apologize for that. Okay, so basically what you see here in the upper graph is it's showing on the right. So the yellow line is the random reads coming from the US. The yellow is Asia, random reads from Asia. The blue one, so the second line from the top, is Europe, and the lowest one is US. So as you can see, like the US random reads for a global instance is 9 milliseconds. These are point reads. And for Asia, it's 165. And for Europe, it's 114. So these are strong reads, okay? Now, if we look at time-bounded ones, we see here all of them are below 10 milliseconds. So this is the power of time-bounded reads. These time-bounded reads have like a staleness up to 10 milliseconds, 10 seconds, apologies. They have a staleness up to 10 seconds, but all of them are served within 10 milliseconds. So that is the power, especially if you want to filter your data, you can use that very nicely. Now, if we look at the multi-region continental, what you see there is pretty much very similar times. But now, as you can see, the random reads are 185 milliseconds. So we had before like 140 milliseconds. So the reason for that is the data has always to be shipped to my clients in Asia because they don't have a read-only copy. So this, like, just even for these point reads, it makes like a 40 milliseconds roughly difference by having this read-only copy in Asia, in the local region. Now I want to show one more thing, if it is working. Let's see. Yep. So here I'm displaying basically, again, random writes. So we have here writes from the US about 30 milliseconds. This is going to a regional instance. From Asia, around 200 milliseconds, and from Europe, about 130 milliseconds round trip time. The sequential writes right now, it has started, is about the same. Now, if I would put that up, it takes a little bit of time. You basically would see that Spanner tops out at like 35% of usage in your instance, because I'm basically always hitting the last bit. So the throughput that I would get for the sequential writes is much lower, even though I have the same amount of compute resources available. All right. So last but not least, related sessions. There is a session right now which you have missed, so thank you for coming here instead of that session, which is about replacing Oracle with Cloud Spanner. You can watch it on YouTube. We will be recording all these sessions and we're putting them up on YouTube, so you might not have missed it out completely because you can basically go back and watch it at 2x. Tomorrow is a session about migrating Cloud Spanner, which is talking about migrating from an SQL database. In that case, I think MySQL that they are talking about. We have also another session in this afternoon where Bandai Namco, a games company, a Japanese games company, built from the ground up on Cloud Spanner a game. Really interesting. I worked with them last year at Next Tokyo. I really recommend going there. And then tomorrow is also like what's new about Cloud Spanner from the PM, Dipti, who is talking about basically roadmap features. And last but not least, a little bit advertising about myself. Please, if you are interested in like ongoing topics around Cloud Spanner, I have a video series on YouTube, which is called TIL about Cloud Spanner. So you see that here, which basically means things I learned about Cloud Spanner, or today I learned about Cloud Spanner. You pick your favorite. You can scan the QR code. You can also follow me on Twitter under @HostyRosty. I'm mostly tweeting about technology, very rarely about like personal things. And with that, thank you very much for attending my talk.